In this video, I will give a basic overview of how optics work and answer questions such as: why does your phone camera need a lens to take an image? Why do some people need glasses? The world around us is filled with light from a spectrum of colors. When a ray of light of a certain color traveling in a straight line hits a photodetector, its position and color are registered. What I'm calling a detector could be cells in your eye or photographic paper, but for now I will talk about the kind of detector you have in your cell phone or webcam. Just as the screen you're looking at now is made up of individual pixels emitting light, the detector in a digital camera is made up of a grid of pixels which can sense light. Alice takes a detector when she goes out and then sees a strange sort of traffic light with a red light bulb at the top and a blue bulb below it. Alice holds the detector up to take an image of the lights. The image will be an accurate representation of the real world if the top pixels are red, then there's a gap, and then the bottom pixels are blue. In reality though, light spreads out in front of both the red and blue bulbs and illuminates all of the pixels at once. Every pixel is equally red and blue, so the image appears to be all purple. This is why we need an optic to focus light. I will go into more detail on what it means to be in focus later on in the video, but for now, think of it as when the red and blue light go to separate points on the detector so that an image has the two bulbs separated rather than just be completely washed out with purple. The simplest solution to this problem is to put a box around Alice's detector to block out stray light and put just a tiny hole, often called a pinhole, in front of the detector. The pinhole blocks out all but one of the red and one of the blue rays of light so that they fall on different parts of the detector. The bulbs are separated in the image, which is exactly what we wanted. The image has become inverted because light from the bottom blue bulb has gone to the top and vice versa. But that's okay, this actually happens with most optics. We can always use the computer to invert it back or wire up the detector to take account of this inversion. Your brain has naturally adapted to compensate for this effect in your eye. This type of darkened box with a pinhole is one of the first optical tools to be used to actually record images. The modern word camera comes from the Latin phrase camera obscura, or dark chamber. Here is an 18th century illustration of a camera obscura with a pinhole. The pinhole camera illustrates the two main properties every optic must have. If the pinhole is large, too many rays get in from each of the bulbs, and eventually it is as if we are back at the start with no optic at all. If we make the pinhole smaller and smaller, the amount of light getting in decreases and the image will become darker until it fades completely. The problem with a pinhole camera, therefore, is that it is a trade-off between how much light gets to the detector to actually create the image, often referred to as the size of an optic's aperture, and the degree to which the direction of the rays is restricted. This is the resolution of the optic, which I will mention later. Ideally, we would want plenty of both. Other optics consist of mirrors which reflect the sources of light onto the detector. With a plane mirror, as you might have in your bathroom, light reflects the same way as a ball bouncing off a wall in a game of squash. How a ray of light is reflected depends on its direction, with the angle of incidence equal to the angle of reflection, relative to a line pointing out of the mirror called the normal. On its own, a plane mirror won't help us avoid the problem of the two bulbs turning the whole detector purple we saw earlier. Instead, the mirror must be curved either into a part of a sphere or into a special shape called a parabola. What this shape of mirror means is that when rays from the two bulbs come in, and they do so at different angles, they are reflected to different parts of the detector. In fact, all the blue rays go to one part and all the red ones to another. Just as with the pinhole, the image is inverted, but light from the two bulbs goes to separate parts of the detector as required. This setup solves the main problem of the pinhole, because you can make the mirror as large as you like in principle and therefore collect plenty of light while still forming a clear image. However, the main disadvantage of this type of optic is that it's cumbersome and very long, due in part to the light being reflected back on itself. For this reason, this setup is mainly used for telescopes. The telescope tube forms the dark chamber to block out stray light, and usually a second plane mirror is added just to divert away the light to the detector. The first known working mirror telescope was made by Isaac Newton, and more recently the Hubble Space Telescope used a similar but slightly more complicated arrangement. This brings me on to lenses, a type of optic which uses refraction. Imagine that you have a truck running on a hard road and suddenly it hits the edge of a muddy field at an angle. For a moment, only one of its tires is on the mud, so one side of the truck slows down while the other continues at speed. The truck turns. In a similar way, light bends or refracts into a dense material like glass, and refracts in the opposite direction when it transitions from glass to air. With a rectangular glass block, the light enters and leaves going in the same direction, just shifted slightly. Having the two opposite sides inclined alters the direction of the emerging ray in proportion to the slanting. By curving the shape of the glass in a similar manner to the curved mirror from before, rays of red and blue light will likewise be diverted to different parts of the detector. Just like with the mirror, a lens can be made larger to admit more light while still maintaining a crisp image. The advantage of the lens is that it allows a practical and compact optical device, such as the human eye or a cell phone camera. The lens is at the front to focus light, there is a chamber to block any stray light, and the detector is at the back. This makes the lens into the most ubiquitous and important type of optic. Usually a high-level optics textbook or a class would talk about what happens to a single point of light. They talk about things like the point spread function of an optic, the pattern of light that a point source produces on a detector. This is because we can always take objects, things in the real world which are sources of light, and break them up into a large amount of individual point sources. As long as the optic works on just one such point, it will also work for any number of others which make up a whole macroscopic object. For an optic to focus light then is to take in a number of the rays that diverge from a point source in all directions and to redirect them using reflection, refraction, or other ways I haven't mentioned to a single pixel on our detector. I will talk only about lenses from now on, but the same arguments apply to other optics like the Newtonian telescope I mentioned. Based upon their shape and other properties, every lens has a so-called focal length. When the point source you're observing is very far away, almost infinitely far away in fact, then this is the precise distance behind the lens that the rays converge and the light is focused. This is therefore the precise distance at which to place the detector behind the lens. If you put the detector too close, then the rays of light haven't yet converged on a single point. If you put the detector too far from the lens, the rays have begun to diverge again. Both cases show what it means to be out of focus. Each point of light now spills over multiple pixels and the whole image becomes blurry, as you can simulate with the blur tool in many image editing programs. The closer the point source comes to the lens, the further the focus moves behind the lens. There is a precise mathematical relationship between the focal length, the distance from the object to the lens, and the distance to the resulting focus. This shifting of the focus is a problem if you have just set up your detector exactly one focal length behind the lens to image things in the far distance, and now want to image a closer object. Cameras and eyes overcome this issue in two particular ways. When taking a photograph with a camera, once the object to be focused on has been selected, the lens will be moved by the photographer or automatically by the internal circuitry of the camera to pick the right distance between it and the detector. The size of the human eye is fixed, so instead, muscles change the shape of the lens and therefore its focal length to shift the focus backwards or forwards as required. In this way, the light-sensitive cells in a layer called the retina, which is the detector in your eye, can stay where they are. Try to hold a pencil close to your face. You can either choose to focus on the pencil, in which case the background goes blurry, or vice versa. Either way, your brain is automatically using muscles to stretch or compress the lens in your eye to achieve the correct focal length to focus on what you want. As I've just explained, if an object is far away, then light is focused close to the lens. For some people, no matter how much their muscles try to adjust the lens, they can never shift the focus of a distant object backwards far enough onto the retina, and they are nearsighted. Conversely, when objects are close, some people can never quite manage to shift the focal point far enough forward, and they are far-sighted. Glasses or contact lenses can correct for these problems. In the far-sighted example, the problem was that rays of light were diverging too strongly from a nearby object, but an additional lens can bend the rays inwards as if they were coming from a distant object. For nearsighted people, the lens makes rays diverge as if the object were closer. Other optical instruments like binoculars also bend the direction of rays using a combination of lenses to make objects appear as if they are closer and therefore more magnified. No optic is perfect, and therefore rays of light are never totally focused. Pixels in digital cameras are small and getting smaller, but an infinitesimally tiny point of light will always appear to have at least the size of a pixel. Both of these effects together mean that two separate points of light, if they are close enough together, will appear to merge into a single point. The resolution of an optical instrument is a measure of how close together they can get before they can no longer be distinguished. Thinking of objects as collections of many point sources, the resolution determines how sharp features in the image will be, or how small or far away an object can be before it blends into the background. One thing to keep in mind is that most objects do not give off light themselves, but merely reflect it. All matter reflects light to some extent. What you might think of as reflection, seeing a light bulb reflected in a plane mirror for instance, is technically called specular reflection. The mirror is polished to a smooth surface, so that the rays neatly preserve their order. Whereas reflection from a brick wall is called diffuse reflection, because the roughness of brick scatters and jumbles up rays from the bulb and from other objects in the room. Also, unlike the mirror, the brick preferentially absorbs some colors, allowing ones like brown to be reflected. Thank you for listening. If you are interested in how a computer works, stores information, and displays images, there should be a link on the screen now. If you have any questions about optics or any other topics for me to cover, please leave a comment. I did not cover advanced topics such as diffractive optics like Fresnel zone plates, nonlinear optics, or optical fibers. I can make follow-up videos if there is enough interest.